Okay, my friends, so here's example 3. We're doing the ice cream sales at the Beach Snack Shack. All right, so this is where it gets, I think, more realistic. This is where the last few examples are fine. But this is where, when people talk about modeling in math classes, they're actually talking about this kind of modeling, which is real life data. I don't know where this data came from that Becky's using here, but the idea is you can actually collect this data based on your own experiences. So it looks like here they've got a daily high temperature and then daily ice cream sales correlated with that. And the question is, well, first, make a scatter plot. Does it look linear? Well, I don't know. We better make a sheet here. So what I'm going to do is I'm going to open up a Google Sheet here. Give me a sec. Let me get this thing open. All right. Now, let's see. I got to pull this data in. So let me see. I got daily high temperature in Fahrenheit. Make sure it's Fahrenheit. These numbers mean very different things when it's centigrade. And then ice cream sales daily in dollars. Okay. Got everything we need out of that document for right now. Let's blow this up. All right. So now we're focused on this. I want to center everything because I'm kind of a dork when it comes to that kind of stuff. And now we're going to make a scatter plot. If you had me in 98, we did this towards the end of the course. Not much, just a little bit. It's a great way of, this is called bivariate data, just like the stuff we're looking at before. You've got an independent variable, which is temperature, and then a dependent variable, which is your ice cream sales. I'm going to grab all the data, including the labels, and then I'm going to go to Insert Chart. And usually Sheets gets the first, it got it right this time. I'll be damned. Sometimes it doesn't. Sometimes it guesses the wrong kind of chart, but this one's definitely correct. All right, this is the daily ice cream sales. Now, the first question I asked is, does this data look linear? Now, the answer, in my humble opinion, is yes, it does. Because it looks like there is a line suggested through the points rising left to right. Is it perfect? No. As we've talked about in class, when the data looks too perfect, it means Indiana Jones is running from the one-armed man and the fugitive. No good could happen. So what it looks like to me is there is some kind of a linear relationship. It's suggested by these points. Then the question is, where do you put the line? I mean, is the line like here? Is it here? Is it here? There's all kinds of places you can put the line. Good news is we don't have to worry about that. Sheets can find it for us. So you double-click on the chart once you have it. And then you come over to Customize, go to Series, scroll down until you see something called a trend line. And when you click that, my dear friends, is the best fitting line. Now, I'm going to also include a video under here, under this series of questions, that explains why it's called a best fitting line. It's actually technically called a least squares regression line. And the least squares part is not important for 105. But if you're interested in a deep dive, you can check out that video. That line best describes the behavior of the points. Notice it goes through, it looks like maybe one. It misses them all a little bit, but the idea is it misses them on average the least amount. I'm also going to scroll down here and turn the equation on so I know what that looks like. And then once we have that, we can go back and answer some of the questions that are actually in the homework. It looks like 16.5 times x plus negative 850. We'll talk about that in a second. If it looks linear, how is it linear? I think we talked about that already. If it looks linear, what does the slope tell you? Okay, let's go back to the slope and look at that again. Okay, so right there. The slope is that 16.5. But remember, and Sheets isn't smart enough to actually put a unit on that 16.5. 16.5 is a rate. It's a per. So then the question is, what is it per? Well, 16.5 is the dependent variable's unit. That's dollars. Per is 1, and that's the independent variable's unit. That's degree Fahrenheit. So what that number right there is telling you, 16.5, is that for every 1 degree Fahrenheit increase in temperature, the number of sales, or the amount of sales, goes up $16.50. Approximately. It's an average. It's not exact. It's an average. So for every 1 degree increase in Fahrenheit degrees, the total sales daily go up $16.50. That's what it tells you. Now, another fun question is, what does the y-intercept tell you? It tells you absolutely nothing. It tells you nothing. It tells you if it's 0 degrees, the company's going to lose $850. That's silly. That doesn't make any sense to talk about. So we'll come back to other things that don't make sense here in a second. All right. So now that's the equation. 16.5 times x. X is the horizontal. X is the independent. That's the degrees Fahrenheit, daily high temperature. Plus negative 850. And again, there's y-intercepts, generally speaking, in most cases, aren't very important. The slope is way more important than the y-intercept. This is a great example of a y-intercept that's not important. However, I do like the equation having it there. So I'm going to go, I'm going to write it here. Google. I'm going to put negative, this is a space holder for now. 16.5 times x minus 850. And don't worry about that. I'm putting that there so when I go back to the notes, I can just go straight to the calculator when I'm done. Okay. What would sales be if the temperature were 80 degrees? Okay, so 80 is not on here. It jumps from 77 to 82. So let's jump in there and actually do this. Let's jump in and grab, that would be a temperature of 80 degrees here, right? So, and I have a negative sign, that shouldn't be there. Actually, let's see how, I wonder if Google can handle if I put dollar signs there. See if it can handle it. It can. It predicts about $470. Okay, so now $470. Let's see where that slots in with the notes. So 77, it's at 412. 82, it's at 522. I'm gonna just put a little thing here and put 80, and then 470. That actually slots in pretty well, doesn't it? That looks just about. Yeah, I'm gonna bold italicize it so we know it's a predicted value and not a real value. Okay, yeah, that's pretty cool. I would add it to the scatter plot itself, but if I do that, it's actually going to change the line because this line is based on the points that I put in this chart. So if I add that point to the chart, it'll change the line. I don't want to do that. So, okay, back to the notes. How about 32 degrees? Well, mathematically, we can totally do this, right? We can just go to our Google calculator and change the 80 degrees to 32 degrees. And it's going to predict a loss of $322. That's what that means. But does that even make sense? Like, that doesn't make sense. Who the hell is going to who's going to be selling ice cream on the beach when the high temperature is freezing? Nobody's going to be doing that. So this is kind of a silly question about, it's extrapolating, right? It's kind of silly to talk about that. How about 100 degrees? Okay, so now 100 degrees, 32 is definitely ridiculous for a couple of reasons. First of all, because it's freezing at the beach, and who the hell buys ice cream then? But also, you see where the data is? It starts at 63 and goes to about 87. 32 degrees is off the bottom end of this chart. Nobody says that this data is going to continue behaving this way if you get far away from the data values you see. So 32 is off this end. 100, conversely, is off of this end. Now, but the thing about it is, 100-degree day is not really all that unusual. So could you see them making about $800 on a 100-degree day? Yeah, honestly, a super hot summer day, somebody just wants to cool off quickly. Even though 100 is off the chart going, above 87, I think topically, from the context of temperature, I think it's realistic. 32 degrees? Hell no. Hell no, 32 degrees. Nobody's going to be selling ice cream on the beach at 32. Selling ice cream on the beach at 100? Yeah, I think that's legitimate. So I think this question is a little bit silly, and I did that intentionally because I wanted to talk about it. This one, not so much. This one, I just did because I'm a Ray Bradbury fan. Yes, could you get a number for 451 degrees? Of course you can. 451 degrees. You can change this to 451. Press enter, and the beach snack shack is going to make about $6,600. Unfortunately, if it's 451 degrees out, that's the temperature at which paper burns, and you're going to be dead. That is a pure extrapolation that's just silly. So you're starting to see with statistics, and this is where statistics gets interesting. When you have data like this, background context is important, right? So this is the data. Let me delete this one row in that I just put in here because it's not part of our data. Delete cells, entire row. Context is important. This is data from the Beach Shack. they then can know how far outside of these temperatures you can go and still have it be a realistic question to answer. Was 80 degrees realistic? Absolutely. That's still within the data. Was 32 realistic? No, because they're probably going to be closed. How about 100? 100's outside, but 100's within the realm of what you would experience at a beach on a hot August day, especially on the East Coast. 451? Hell no. So, my dear friends, I think you've got enough to give the homework a shot. So go give it a shot.